Alright, so look, we finished, you'll be pleased to know, the mechanics part of the course, which I know was long, was difficult, there was lots of formulas and lots of English in it, so that's good news. We're going to start part 2 now of the course, which is materials.
Would this be a little bit slower?
Yes.
So
Yes.
it's like we're done with the stuff.
So,
So we're done with everything calculated. Those letters.
Kinematics.
yeah.
Questions
So like we're done.
If you want.
We're done like we're done.
Yeah, mechanics part's finished.
So we're done with the hardest part of physics.
So we're now doing materials now.
Is it harder than before? What we just
No, mechanics was the hardest part. So materials is easier. I know, so it's good news. It's good news, right?
Yeah.
All right. Can you write this down? Density.
Okay.
Can you see okay?
Yes.
Yeah. Okay. Do we need the light off or is it okay? Is that right? Yeah, okay, fine. You prefer it off? Yeah. Yeah, I think so. It's a little warm. Yeah, a little bit. Okay, so density. You remember we actually touched on this a little bit earlier in mechanics. You remember I think we actually did it in the first lesson, didn't we? So we'll just recap the formula for density. Well, actually, what's the definition? Do we remember it? Density is... Yeah, as a formula, it's mass divided by volume. How would you put it in a sentence, though?
The measure of mass per unit of volume.
That's it, the measure of mass per unit volume. So, that is mass over volume. Okay? What is the dimension?
Cube.
The dimension. Not the units, the dimension.
Dimension.
No.
Yeah?
No.
Or dimension.
No, the dimension as in like mass length.
Mass.
Mass?
Length times breadth times height.
No. This.
Meters.
Density is mass or weight.
No.
Oh.
Come on, I know you know this. I know you know this.
kg.
Area. Mass.
That's unit. I want the dimension.
He done has
Meters
LT.
per meter.
That's the unit.
We done
Alright,
has-
if you're not getting it, I'll tell you. The dimension is mass per length cubed.
That's volume.
Yeah.
So it's mass per volume.
Yeah, but volume wasn't the dimension. Remember we had, what were the dimensions? Mass, length, and time.
Okay.
Yeah, so this one is mass per length cube.
Or
Yeah.
LL per cube.
And what's the units?
Kilograms.
Meter cube.
Meters and negative.
Kilograms
Meter cube.
Negative.
per...
Per meter cube.
Oh, come on.
Meter cube.
Kilogram per meter cubed. Yeah?
Yeah.
So cube or cube?
Cube.
I just want to be sure, like, I keep hearing cube and I keep hearing cube, so like, I'm not sure.
With a D at the end. Yes, okay. So the dimension is mass per length cubed with units of kilogram per meter cubed. Ming, come on. And who's with you? Come on. Where's Son?
It's coming.
Probably buying coke.
Come on. We're doing an hour of physics and then maths, okay? Alright. Right, can you write that down? Especially the second part. You seem to have forgotten that. About the dimension and the units. Alright. A bit sleepy, huh?
Chemistry.
Oh, you have that test today? Some late night studying perhaps? Yeah, okay.
3.
One.
Not good for morning class. Alright, do you have that? Can I go to the next slide? Yeah, okay. So we kind of know already what density tells us. As you said, it's mass per volume, right? Okay. Some materials have a high density. Can anyone give me an example of a material with a high density?
Diamond.
I'm not sure how high diamond would be. I'm sure it's pretty high, but I don't think we can think of something higher density.
Diamond.
He literally just said that. Something else. A metal. Well, what's a metal with a high density?
Steel.
You're right,
Instead.
Yeah. Oh, just something expensive, like gold, for example.
Premium.
Yeah. Yes. These materials. Gold.
Mercury.
Mercury has a high density as well, doesn't it? Yeah. Especially for a liquid, isn't it? At room temperature. Yeah. Gold has a very high density. Very high density. It has a density of 19,320 kilograms per meter cubed. So what that means is if I have a meter cubed, then how much gold do I have? 19,320 kilograms, which is an awful lot, right?
The gold is in solid or liquid.
In this form, solid, I'm talking about, yeah. Okay, you don't need to write that down because I have values coming up in a moment. As a quick revision question, let's see if you can remember how to do this. Can you convert this from kilograms per meter cubed into grams per centimeter cubed? Let's see if you remember how to do this. Nope.
Okay.
It's been a long time since the first lesson, huh?
Kilos times power.
19.22.
Oh, well done. 19.32. 19.32. Do you need to see that, or is it okay?
Let's see.
Well, we'll do it quickly, okay? So, 19,320 kilograms. How big is a kilo? Oh, sorry, kilograms per meter cubed. How big is a kilogram? 1,000, 10 to the 3, isn't it? 1, 2, 3. And then what do we do here with meter cubed? Meter cubed. Do we want meter cubed? No, what do we want? Centi cubed. And so what must I put up here? Centi cubed, good. And how big is centi? 100. Yeah, 10 to the power of minus 2, isn't it? So this would be 1932000 times 10 to the minus 2 cubed centimeters, grams per centimeters cubed. I lost my grams there. Who did I get? Son, come on. Anyways, that works out to be 19.32 grams per centimeter cubed. Okay, but we did this in the first lesson. Yeah. So I'll continue. Right, give me an example of something with low density. Say again? Ah, no, even lower than this.
Oxygen.
Lower than this. Plastic? Plastic has a low density.
Yeah.
I'm thinking of a, I'm thinking of a gas. Helium. Helium has a very low density, doesn't it? Yeah. Compared to gold, it is 0.179. Now remember how much was gold? About 19,000. And this is less than 1. So you can see how low the density is here. So if I have a meter cubed of helium, then what will be the mass? 0.179, isn't it? Yeah. Pretty small, right? Okay. What about something that would be medium density? Water would be considered a sort of medium density, okay? And does that, I'm sure some of you know, the density of water? What is it say again? No, I think you're thinking of something else. What is it? Yeah.
1.0
Yeah.
kilogram
Yeah.
meters minus 2.
No. Nice try though. You're a little too small. Not 1.0.
100.
997 kilograms per cube.
That's just off the top of your head, huh? It's roughly 1,000.
1 ton per meter.
Yeah, it's about 1,000 kilograms per meter cubed. I think what you were thinking of was 1 gram per centimeter cubed. Yeah. So for water, it's about 1,000 kilograms per meter cubed. Now it changes, of course, if it's like salt water or fresh water or things like this. Okay. And the value of the density of water is actually an important value in science. It's so important that we use it as a definition. We have something called relative density. For example, gold was 19,000 kilograms per meter cube, right? That makes it 19 times denser than water, because water was 1,000 kilograms per meter cubed. So this gives us our next idea. It's actually good to compare density with water. It gives us something called relative density. Has anyone ever heard of this? Relative density. Relative density. You've all heard of density, but maybe not relative density. Yeah. So relative density, which is S, is the measure of density of an object compared to water. So for example, it's the density of the object divided by the density of water. Yeah? So if something has a density of 2,000 kilograms per meter cubed, what's its relative density?
2 times.
2. 2 times that of water, yeah. Yeah. Oh dear. Now, do I have everyone now? What's his story? Do we know?
It's coming.
Is he? Okay.
I trust him.
Far away from here. Maybe.
Does he? Far away?
Yeah, maybe
Really?
because the bar.
Blanchardstown's quite far, I suppose. Right. What is the dimension of relative density?
Doesn't have.
Very good. Very good. It doesn't have a dimension, does it? So, does it have any units? No. No. It's dimensionless. Yeah? Okay, good stuff. One example of the use of relative density is in buoyancy. Does anyone know what I mean when I say buoyancy?
Things float.
Floating or not. So how does relative density link into whether things float or not? Do we know?
If it is more than the density of water, it will not float.
Good, yeah. So if the S is more than what value?
1 P.
1. If S is more than 1, what happens?
Sink.
Sink. If S is less than 1,
Float.
it'll float, yeah. If it's less than 1, like wood, what happens when we place it in water? It'll float. And if it's more than 1, like gold, what happens? It'll sink. You all knew this already. This is like basic middle school science.
So why do like ships?
Their density actually is less than 1. Because although the steel is quite dense, most of the ship is just full of air. It's empty. You know, it's not like the ship is packed solid. It's not like a solid block of steel. Do you know what I mean? It's hollow, yeah. So it's actually, in total, its density is less than
Why
1.
don't we stand less than 1 and greater than 1?
What do you mean?
I thought it was either less than water or greater than water. What we say?
Well, S is less than 1. That must mean that it's...
Okay.
Yeah?
Okay. After you divide.
Yes, after you divide, yeah.
No, I'm talking about like those ships that carry cars, containers, airplanes.
Yeah, still, but like
The
even
same
if you
thing.
think, even if you think about a car, like although it's made out of steel, it's quite hollow on the inside. So in total, its density will be relative density will be less than 1. Well, maybe not for the car itself, because I think about cars tend to sink, but the ship in total will be less than 1. You know. Okay. Continue. Oh, and the other thing that's interesting here, like with the wood, Do all pieces of wood have a relative density less than 1? No, actually. There is one particular tree where its density is more than 1. I can't remember what it is. It's like an ash or something. Anyways, there are some trees where the wood is so dense that it actually sinks.
Ebony.
You found it? What is it?
Yeah.
Where does it grow?
So like it's the one. It starts from 1 like at ebony wood like
Oh, okay. Ebony wood is S equals 1, is it?
1.1
Alright.
to 1.3.
Oh, okay. So that would sink then. Interesting. Okay.
And green heart is 1.04.
Okay, so these would all sink then. Grand. Okay. Next now. So you'll need to write these down. These are some values of densities. A couple of them you've seen already. So the first one is gold. Then we have silver, nickel. Now, you know with salt water, what's interesting about salt water?
Additional 30.
An extra 30, isn't it? Yeah. Fresh water. What about ice? More or less than 1,000? Very good. A good bit less, isn't it?
But why is it less?
We'll get to that in a second. Alcohol? More or less than water?
More because it's also not pure.
Less. Wood? Now, as you were saying, it's different for each tray, but like an average value would be something like 700 here. Now we're going really small now. Air, 1.2. That's really small compared to everything here, isn't it?
Well, air is a mixture of gases.
Yeah, so like just an average density. We'll actually do an example in a moment where we mix two different things. Yeah.
Do you have to remember that?
No, that would be too demanding. Well, I would say actually the only one that you would be expected to know is which one?
Water.
Yeah. Okay, do you nearly have that? Yeah? Relative density of salt water, more or less than 1. You can see it's more than 1. So what would happen if you mix salt water with fresh water? What would happen to the salt water?
To be at the bottom.
It would be at the bottom, yeah. What happens if you mix ice with fresh water or salt water?
So it floats.
It'll float, right? At what temperature is water most dense? Does anyone know this? At what temperature is water most dense?
Above 100 degrees.
25.
No.
100.
No. Because actually you can...
Four.
You got it, okay. You knew it was one of those. At 4 Celsius, if you heat water to 4, that's the most dense it can be when it's at a temperature of 4 Celsius. Yeah. Which is kind of strange, isn't it? So if you mix water at 4 Celsius with, say, water at 2 Celsius, what happened to the 4 Celsius water? It would sink, wouldn't it? Yeah. The warm water would sink to the bottom. You're looking shocked at this.
Because I don't know how someone sat down to do all this.
Say again?
Like, I really don't know how, like, people are just, like, calculate this and, like, sit down and, like, do this.
You can do. No, you can do this. It's not too difficult to do.
Because, like, I don't know how did they know that water did not mix and water salt.
Huh? What is-
How did they know that the water did not mix but it sunk? Like,
Oh, so what you could do is you could take the water at 4 Celsius and colour it. And then mix it in with water at 2 Celsius. And then you can see it sink. Yeah.
but the color will like add more.
But that's why you don't use a colour that would affect it much. You know, this is really not a big problem to figure out to fix. Yeah. Okay, do you have those values? Yes? Alright. Okay, here's a question which I hope you can do quickly. And I'll run through the answer with you. So you have 1 litre of fresh water is mixed with 1 litre of salt water. Convert 1 litre into SI units. So I want 1 litre converted into meters cubed. Now, do you remember what the rule is for a litre? How big is a litre, or how can you convert it into meter cubed? No. Because think about it, 1 litre is quite small. That could, yeah, what is it? Oh no, I thought you had it.
1,000 centimeters.
No.
1 milliliter equals 1
Oh, no.
centimeter.
Yeah, okay. 1,000 litres equals 1 meter cubed. 1,000 litres equals 1 meter cubed. Yes? Yes, no? Yes. Let me write that down for you. 1,000 litres equals 1 meter cubed. So what would 1 litre equal? 0.001 meter cubed. Yes? Yes? Okay. Okay, so now that you have that, I think you can give me the answers here. So just take a minute to run through these. They're very short, so just write the answers down. It'll only take you a few seconds for each part. So we have the first part done already. You'll need your calculator maybe for the last part. Okay, you nearly have it. Rahman, I see you're nearly finished. Or finished. Just checking the last part.
Yes.
Yeah. Aoife, which part are you on? Will we run through the answers now? We can do them together. Marwan, which part are you on?
Just check.
You stuck a little bit?
Not sure.
Okay, well let's check the answers together. Okay. So what's the answer for part A? We said it earlier, it's 0.001 meter cubed. Who got the mass of a litre of fresh water? What is that?
1 kilo.
Very good, 1 kilogram. Very good. The mass of 1 litre of salt water?
1.0.
Very good, 1.03 kilogram. The combined mass, if you mix the two together?
2.0.
Obviously 2.03 kilograms. The combined volume? Very good, 0.002. And so the last part is the only kind of tricky part. It's the combined density, which would be the total mass, which we said is 2.003, didn't we? And over the total volume, which we said is 0.002. Wasn't that what we said? Yeah. So what do we get here? 1.0015, was it? Is that right? Or have I done something wrong?
The mass is 2.03, not 2.002.
Yeah, I think.
Oh.
So it's
Oh, I have too many zeros, do I?
supposed to be just 1,000.
2.03 over 0.002.
Yeah.
Is that what we said? Yeah, okay.
So it's supposed to be 1,015.
1,015 kilograms per meter cubed, or 1.015 grams per centimeter cubed. Which do we prefer, kilograms or grams here? Yeah. Although I'm just showing you this because I think in chemistry maybe you use grams and centimeters more. You don't? Not yet, anyways. Okay, fine. Well, we try to stick with this one here. Okay. Next one, you don't write this down. This is just a multiple choice one. I've seen it on a quiz before. A student places a 10-gram ice cube into a glass of water. The water is to the top of the glass, and the glass of water is left out on the kitchen table, and the ice then melts. So just a quick picture here of what we got. So you've got your glass of water, and it's right up to the top. And floating in the top is your ice cube. And there's, you understand, it's right to the top. There's no spare space. Okay? And the ice melts. When it has fully melted, what has happened to the glass of water? So I'll give you three choices. The volume of the water in the glass has increased, and so the water, it overflows. Okay? Or the volume of the water in the glass is unchanged. So even though the ice has melted, it's still to the top. It hasn't changed. Or lastly, the volume of the water in the glass has actually dropped. So the water level has dropped, and you have now a little bit of space on the top. So what do we think the answer is here? A, B, C.
C.
You're going with C, that the water has dropped a little bit when the ice has melted. Good, okay. Anyone else agree? No? You're going with the volume, it's overflowing, so the water has gone out the top. Okay, so C, A. Anyone else? You're going with A, okay. So we have 2 for A. Okay, good. So we have all 3 answers possible. B. Anyone else? B. Oh, good. We're getting a consensus now. Or none of these is a possibility, yeah. B is the correct answer. It actually, the water level is unchanged. Yeah. The calculation is a little bit too difficult for this course, but if you were to do this experiment, if you were to put some ice into a glass of water and fill it to the top and let the ice melt, in fact, the water level doesn't change, which is quite interesting. Because you might think it would overflow.
What if you put this in a drink, you change taste? Sorry. The taste changes.
The taste changes, yeah.
Okay.
Yeah.
So
So
the
like, doesn't, it shows that the ice has to feel like it's in the water.
Oh, yeah, but not- but doesn't affect
the volume.
But it doesn't affect the volume.
0.0000.
No. It doesn't affect the volume.
But the ice should also have a volume.
It does. So what happens is when the ice melts and turns into water.
It's sort of like sucking some water as well.
No.
So like,
Okay, so look, picture the ice cube in the water. Okay, when the ice cube melts, that volume that the ice cube was taken up is gone, and it gets replaced with liquid water. And it just so happens that the match is perfect. That the volume you lose by taking the ice out because it melts will match exactly the volume that you gain from the water. So what you're tasting is just that the water has mixed with the drink. But the volumes stay exactly the same. I'll draw it here in the picture. Imagine this ice cube was gone. Do you see this bit of volume here? You would have extra volume, wouldn't you? If the ice cube was gone. What happens is when the ice melts, when it becomes a liquid, the amount of volume it takes up will be exactly the same as this amount that's in the water.
But isn't the density of liquid water like greater?
Yeah. Like I said, the calculation is a little bit too difficult for this course, but you can trust me on it. That when this ice cube melts, when it becomes a liquid, it will take up the same space as the volume submerged here.
Does the size of the ice matter?
No, doesn't actually.
So if I like put a cup on the weighing scale and then like I put the ice, I'll see it go up. Then later on it comes back.
No. If you put this on a weighing scales, would the mass go up or down?
It will first go up and come back down.
No. This is going to change. You're not.
It's the same thing.
Yeah, exactly. It's the same thing. You're not adding or subtracting anything.
I know if I'm going to do this.
No, but then like saying the cup is very full like
Yeah.
this, like
To
this
the top,
cup,
yeah.
and then you put ice.
No. You'd have to. Yeah. Obviously, if you
Yeah,
put the ice in when it's full, it'll overflow. So what you do is you get it nearly to the top, and then you start adding ice to it, and just make sure it's all leveled off, and you have the ice floating in on the top. Then, yeah. Obviously, if it's full to the top, and then you put the ice in, then it will overflow. I'm talking about the ice is already in there and it's to the top. Anyways, I'm just telling you this one because it's a quiz question. I've seen it on quizzes before, okay? So it's just a little bit of trivia to remember. Okay, I have one example left to do. Good, okay. This example here is taken from an exam question. So this is what an exam question would look like on this topic, okay? What you have, now you'll have to use the table I gave you earlier. What you have is this. Some silver jewellery is actually a mixture of silver and nickel, and not pure silver. What is the density of a mixture of 10 grams of nickel and 1 gram of silver? Now wait, before you start it, I'll give you a little hint to help you, okay? Do you know the mass of the nickel? Yes. Do you know the mass of the silver? Yes. Do you know the density of nickel? I gave it to you earlier. Do you know the density of silver? So could you know the volume of nickel? And could you know the volume of silver? And could you know the total volume? And could you know the total mass? Then you can know the density. Okay? So I'll give you a minute to try it and then we'll look at it together. Do you not have the table written down?
I made a mistake.
Okay. Okay, how are we doing? I see lots of calculations. Oh, did you not write the units down? The first, that's kilograms per meter cubed, and that one's relative density. Right, let's have a look at this now. Right, did any of you get an answer? No? Aoife? No, not yet. Marwan? Not yet? Oh, okay. Looking for the calculator?
10338.
10338. Sounds believable. Could be true. Anyone else? Rahman? No, yeah. Okay. Well, let's have a look. Let's have a look at it. Okay, guys. We'll do this one together now. Okay. I think some of you maybe have it or nearly have it. Anyways. Okay. So the density of the mixture equals the mass of the mixture over the volume of the mixture. Now, one of these we know straight away. What one do we know straight away? The mass, yeah. What did I say? It was 10 grams and 1 gram, wasn't it? So what's the total on the top here? 0.011 over, and the mixture. So that's the volume of the silver plus volume of the nickel, right? Now, do we know the volume of the silver or the nickel? No. But we can use this formula. Density is mass over volume. So what does volume equal? Mass over density. So if I rewrite this, I have 0.011 over volume of silver. I can rewrite this as, did I do that right? Yeah. Right, what was the mass of the silver? 0.001. And what's the density of silver?
10,500.
Okay. And then the volume of nickel, according to this formula, is mass of nickel over density of nickel. The mass was, I think we said 10 grams, wasn't it? And what's the density of nickel did I give you?
8,900.
It's
8,900. Okay, bash that in on the calculator and let's see what you get. So can you bash that in? Oh, you have it? It sounds a little bit small. Let me just check with this. 0.011 over. Let's see. 0.001 over 10. 0.010. Sorry if I think your answer was not quite right. I don't think you said this to me, did you? 9025? No, okay. 9025, yeah? I got 25 here. 9025
Yes,
kilograms per meter cubed. You got it, yeah? You got it? Good job. Now, I think after you see this done, you realise it actually wasn't that hard, right? It was just which way to be thinking about it. You can see you can actually get it done pretty quickly. Getting cold?
Yeah.
Okay. Are you all happy with how these types of questions are done now? Yeah? Because like I said, this is an exam question. I think this was a Section 8 question a couple of years ago. Oh, how many marks would it have been? No, I think more than 2, 3 or 4 maybe. Could have potentially have been 4 marks.
But like, is this really how they do like fake silver? So like the nickel.
Yes, it is. Yeah. They make like a lot of jewellery would have something like nickel maybe mixed in
So
silver.
like,
You know.
this is cheating because like, cause the nickel is way more than like the silver.
Okay, well you're saying that this jeweler here might have mixed too much nickel with the silver,
Yeah.
perhaps. Yeah. This would be low quality then. Yeah. Okay, are we all right with that? Yeah. So look, you got a few minutes left. You can get a start now on the homework. The questions should be similar to this last example here. Okay. Do you want to take out Moodle?